Hello, and my name is Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our November webinar, Fiber Optic Linear Heat Detection and its application in fire detection. We're very pleased to be able to showcase the work of our very active technology committee. This is a webinar that is focused on the committee's work as opposed to an individual company. And so leading off the process is our very active, very able technology committee chairman, Gareth Lees of AP Sensing. Gareth?
Yeah, thank you, Mark. Thank you for the kind introduction. As Mark said, this is a FOSA Technology Committee presentation on fiber optic linear heat detection and its applications in fire detection. The main presentation is going to be given by Julio Toko from NKT Photonics. But first of all, I just want to say a few things about FOSA and the Technology Committee and the activities of the Technology Committee through the year. Could you move to the next slide, please, Julia? Yeah, so FOSA was set up in 2017. It's a non-profit association. It's a group of very active companies in the field of fiber optic sensing. The aim of the association is primarily to educate people on the benefits of distributed fiber optic sensing and the associated technology. As I said, we're incredibly active. We produce a lot of content throughout the year. Part of that content is this webinar, but we also produce papers, and we work with other organisations to push education of distributed fiber optic sensing to anyone. So we're a global company with a global reach. Next slide. So the Technology Committee is kind of one of the core committees within FOSA, and we produce a lot of the documents and a lot of the content which we kind of push out. One of the documents which we produced recently this year was on cable installation consideration. So it was a 10-page document which outlined how cables should be installed for fire detection. And this webinar is actually a follow-on from that document to really reinforce the use of fiber optics as fire detection technology. Like I mentioned, we do have these, we push our members to have these webinars every month. We put them on YouTube. They're available for anybody to go and have a look at, and they're on some fantastic ranges of subjects, and there's a lot of real good information in those webinars. So please take a look at the FOSA YouTube channel, and there's some great content on there. We also try and push forward into external conferences and external organisations. We presented a paper at OFC, the big communications conference, earlier this year, and we're working with API discussing pipeline leak detection technology. And we do have a very active community, and we do meet every month to discuss progress on the different projects we have going. If you just skip to the next slide, Julia. This is my last one. Really, sorry, go back. That's it, yeah. So if you go to the FOSA website, there's a resources section, and if you go to that resources section, it's got a lot of the content which we produce. There's case studies, there's a range of installation considerations, not just for this fire detection technology, but for highways, power utilities, rail and pipeline applications. And again, all the videos and webinars, if you don't have access to YouTube, then they're available on our website. And there's also some technology primers, which we find are very useful, actually. They're 1 or 2 pages, which just outline DTS, DSS, DAS technologies, and they're just very short descriptions of the different technology. So that's me finished. Hopefully you found it a bit interesting to hear a bit more about FOSA. I'll hand you over now to Giulio Turco to talk a bit more about linear heat detection. Giulio, over to you.
Thank you, Gareth. I really appreciate it, Gareth. We are going to talk about introducing fiber optic sensing for linear heat detection. What's very important is we're going to continue what you said there, Gareth. At the end of the day, is what is the general concept is to use distributed temperature sensing, distributed acoustic sensing, distributed strain sensing. The phenomenon is measuring vibration, whether or not it's vibration, strain, or temperature within the fiber, using a standard telecom or standard fiber optic sensing system to measure different parameters. The most important thing is we're going to do temperature, vibration, strain, but it's a very simple approach and concept. The main concept is we are just piggybacking on the fact that you can have a simple fiber optic cable. You can monitor all these three parameters, and you can do it 24/7. So the beauty is that you can have multiple fiber optic sensing components. What that means is it's not, let's say, point sensors, but at the end of the day, it's continuous sensors. So everything is a passive sensors. Everything is monitored in such a way that you can tell within a meter or so what's going on in your asset, let's say. In our case, we've always been doing at FOSA, and I appreciate the FOSA. Thank you, Gareth, for the explanation about FOSA, is that we do pipeline condition monitoring, we do pipeline heat trace monitoring, we do third-party intrusion security, geotechnical. Geotechnical, we're talking about landslides, we're talking about a lot of, we talk about New Orleans, there were dam monitoring, and then a dam that definitely gave up. Part of it is we just need to monitor these, and that's the capability of a fiber optic sensing system. We have transport monitoring, we have oil and gas, whether it's downhole, it's midstream, as well as upstream, as well as upstream. We have structural health monitoring, we have power cable as well. In this webinar, we're gonna focus mostly on fire detection. Fire detection, the question could be from many people in the audience who will say, well, I don't understand how is DTS tied into fire detection. Well, linear heat detection is a device that's been used in the industry for the longest time. What I would like to say is that distributed temperature sensing has introduced a new linear heat detection. That's called fiber optic linear detection. And that's why it falls within the FOSA and all the vendors' discussion about DTS. We'll talk about linear detection. Linear detection, what it is I want to talk a little bit about various types of linear heat detection. We have the conventional one. The conventional one looks on the left, we have the twisted pair, metallic wires. We can be copper wires, single temperature. What it means is if a temperature reaches a certain level, these twisted pair short themselves out, and then at the end of the day, you get an alarm coming back. You also have point sensors, they're called heat sensors. These are discrete sensors. Then you have also the rate of rise sensors on the conventional side. Twisted pair, change of rate. So if the temperature is changing really fast, these pairs actually will get wired faster, and then they give you an alarm. The reason why we are here is to talk about fiber optic linear heat detection. This is very, very, very exciting for me. It's exciting for hopefully everybody in the audience. Fiber optic linear detection is a system where you eventually decide whether or not you're going to use a metal-free cable or a metal cable, variable temperature, and rate of rise. So you get a lot of flexibility in that. So what is a traditional linear heat detection? A traditional linear detection, as I said, is you get the temperature, you get a fire, and then it shorts itself, then you get an alarm. The problem is, I won't say the problem is, but at the end of the day, what you get is you have a junction box and you have an end module. End module is a resistor. That resistor, if the temperature goes up, the resistor is changing the current, and then you get an alarm. The zones have to be set based on the junction box where you do the connection and the end module. In the case of fiber optic linear heat detector, you actually have a laser that gets pulse. If you get two heat locations, for instance, in this case, in this slide, you get a first temperature measurement and you get a second temperature measurement, and that gives you the flexibility and the ability to know exactly pinpoint within a meter where the event is occurring. In the case of fiber optic linear detection, we have definitely a flame retardant FRNC jacket, highly responsible small diameter system. So we really want a system that says, I am detecting the fire or a temperature change or an event as fast as possible. So most of the time you get a cable that has a response time that's as fast as you can get. So at the end of the day, we have a ruggedized cable, we have a dielectric cable. They meet existing UL and ULC and FM rating. These cables are rated in such a way that they can sustain certain temperature, at least up to 900, 950 degrees Celsius temperatures, and survive and tell you exactly what's going on with the fiber. The advantage of fiber optic linear detections are continuous temperature monitoring. This is one of the most amazing things, is that there is no dead zone. I showed in a conventional linear detection approach is you have to set your physical zones. In this case, you don't set your physical zone. You get a temperature measurement every single meter or every single 3 feet, and you can see exactly what's happening within the whole sensing structure or equipment. So in this case, you can reach an accuracy of 1 degree Celsius. You can know within a meter where it is, but most importantly, you also can see the trend of the events. And last but not least, it's immune to EMF, electromagnetic interference. So EMI interference. It's very, very important to point that out, because this sensing cable can be installed in many other areas, as we're going to talk about within the webinar. It will be installed in areas such as cable trays. If you literally use a fiber optic cable that has metal wires in it, that can actually induce more current. So the ability to have this sensing system in comparison to the conventional systems where they have wire and it's active, in this case, it's a very passive sensor. The flexibility of the alarms are extremely important. In this case, we have a continuously sensing fiber optic cable. You can get temperature everywhere. The ability to know what is the maximum temperature, the rate of rise, and the ability to know what is the differential temperature within an area is the flexibility of the system. In this case, what I would like to point out is that if I go to buy a conventional linear detection, I have to know in my mind if I'm buying a 155 degree Fahrenheit, 145 or different Fahrenheit system. In the case of fiber optic, you don't need to know which system you buy. You literally are buying a fiber optic UL rated cable with the controller, with the ability to change these parameters based on a lot of different, let's say it could be a regulation, but it could also be the ability to say, based on what I understand and what I've done in the test, I can change this alarm based on what I've seen. The second advantage of the system is you have, most people have a linear heat detection system, fiber optic, which is a DTS, distributed temperature sensing, and most vendors have up to 4 optical channels. What that means is you can actually monitor multiple things at the same time with one controller. This controller can tie into your fire panel, which I'll talk about later on, So you can have a large building, you can have a bus duct, you can have a cable tray. At the same time, in this slide, you can see a conveyor belt. You can also monitor a, let's say, the roof of a tank, oil tank in a tank farm. And you can also monitor different things. For instance, if you're in a power plant or a oil and gas plant, you can monitor a pipeline at the same time. So that's really the flexibility and the beauty about the system, multiple assets monitoring. What's also important is that we are compliant with the standard fire detection and other standards certificate and certification and requirements. We have VDS, UL, ULC, FM approval, TUV. Most importantly is like when we start talking about tank farms, we also talk about explosion-proof areas. Explosion-proof areas are very, very critical, and to have a system where you don't need to do a physical connection like a standard linear detection, you can just use a fiber optic sensing system and use a cable where you don't have to worry about is the system active or not, because at the end of the day we are only a passive sensors. So that's very important. The next advantage is the ability to have different configuration. One of the best configuration is of the fiber optic linear detection is like we talk an example of a tunnel where you can have a system installed in such a way that you can monitor both lanes of a tunnel, as the first picture on the left shows. The same cable will have two fibers. One within the cable is green, one of them is red, and you can actually monitor both of them. One of them will be in channel number 1, one of them will be in channel number 2. So the third configuration is you get a full redundancy. Full redundancy means what? You can get 2 DTS or 2 fiber optic linear detections controllers monitoring the entire cable and 2 different cables. At the end of the day, if you have a break within a cable, you actually can still monitor up to that point and you have no loss in your fire detection system and alarming system. This is just amazing in a sense of from an engineering point of view, is from a fire detection point of view, is the asset is still being monitored up to that point, regardless of the problems or the fiber break. So what that simply means about the Class A advantage explained is that here's a perfect example, when it's not a case study, but it's a true example of what happened, where we have installed a system in a tunnel. You have about 6,000 feet. I have a picture in the middle showing how these gentlemen have installed the system. On the right, you can see the red cable that we discussed and the green cable, the red fiber and the green fiber that we discussed. There's a mirror image that go lane number 1 and lane number 2. Because of de-icing, a year ago, these gentlemen have used certain tools to remove the ice from the ceiling in these tunnels. Unfortunately, they broke the cable. The beauty is that the software detected a fiber break and gave an alarm. At the end of the day, we still monitor the first lane, the east side, eastbound, I would say, and the westbound. And you only lose so much coverage, which is probably 1 meter or 2 meters of coverage. That is the beauty of a fiber optic DDL detection. The next advantage is the ability to be integrated to a fire panel. Most of the time, we are in the DCS world, distributed temperature sensing world, but most of the time we can hear people are Honeywell, that's a Siemens or Tyco. There's so many different systems. The ability to be UL rated, to have UL relay outputs, is integration to any fiber optic, fire panel systems. The compatibility is just amazing. The third thing is the ability to be having a software that can tell you exactly where the thermal events, because we are measuring temperature every single meter. We can tell you in a map or in your assets. On the left is a map of a subway system in Germany, and then you can see the temperature monitoring. On the right, you can see when it gets too hot or it gets too cold. It also gives operators the ability to understand is this tunnel being ventilated properly or not? On the right hand side is another example where we have an enhanced visualization where it gets very cold or very hot, and you can see where the location of a fire is on the right. So this gives the operators the ability to pinpoint exactly where the problem is and be able to intervene at the right location at the right time. Now, let's talk about the applications of the fiber optic linear detection. The applications are quite interesting in the case that how do we find a way to use this system? It's not a conventional system, and we are working towards explaining to the clients, explaining to the world what the system can do. In this case, we can do tunnels. You have road tunnels, subway tunnels. You have other infrastructure as well. For instance, power cables within a tunnel needs to be monitored for fire detection as well. Let's not only use fire detection, we can use the same tool for also temperature sensing system. In the industrial mining system is the same thing. You have conveyor belt, elevator shaft, cable trays, and cable ducts. This is the #1 source of fire in the mining industry, to have a conveyor belt that can catch fire because the bearings are overheating. We have also other facilities, airport hangar, parking structures, freezer warehouse. Freezer warehouse is a beautiful example of not only you doing fire detection within a freezer warehouse, but you also can tie in with an insurance company to say, I am also cooling my system as well as possible. And then we talk about industrial facilities. We have floating roof tanks, we have power generation facilities. All the time, you have in the power generation facilities, you have motors, you have different let's say fans and different equipment. The ability to run this system or the fiber optic cable and be able to literally change how the fire detection zone is responding for each one of those areas is very important. We also have the nuclear power facilities where we use, let's say, hard rad, which is radiation-proof fiber, to be able to detect different parameters within the system. I'm gonna start with the tunnel. The tunnel is, I do love to ski. Well, I don't like to ski, but I do like to go snowboarding. In Denver, you have a EGMT tunnel, which is the Eisenhower-Johnson tunnel. This is one of the most fascinating story where we install this system. You get about 30,000 vehicles per day at that location. This tunnel is one of the most important tunnels in America. The ability to detect a fire and the ability to prevent a fire, the ability to make sure that this tunnel is not shut down is very critical. In this case, on the right, you can see we have a system where before installing this fiber optic linear detection system in this tunnel, the client had to make sure, which is CDOT, that we are meeting the requirement from a sprinkling point of view, from a camera point of view, from a fiber optic linear detection system point of view, is the ability to detect the fire and suppress that fire. The suppression is the most important key here. We are not trying to put down the fire, but we are trying to suppress it so that somebody can make a decision, or the fire detection crew on site can go in the tunnel and intervene and save lives. I mean, this is in this case, it's very, very important. So on the left, you can see a picture where they installed or did a mock-up of this tunnel to prove that the fiber optic linear detection is the best system before doing the installation, which is on the right. The installation on the right means you have cameras, sprinkler, and the fiber linear detection as the red line on the right. So what they did is, the fire detection approach is very simple. You have a pre-alarm. The pre-alarm is if you reach a certain temperature, because you're monitoring the entire length of the cable from a thermal point of view, the pre-alarm is to activate the camera. The camera will zoom in and show to the operator what's going on. And then the alarm will tell the fans that they need to be activated, and also the sprinkling system needs to be activated. Here's a picture of the alarm, the pre-alarm showing, for instance, a vehicle coming in and the camera is on. And here's a picture depicting when the sprinkling system is going on. When we do these tests and then the ability to try the system every year to make sure that the system is responding, these are the pictures we get all the time. This year, unfortunately, when we install fiber optic linear detection for fire detection, we certainly don't want to have fires. It's just not good for anybody, but we do it for one reason. Number one, it could be a code. We have to do a fire detection system anyway. Number two, we really want to save lives and make sure that people are in a very, very good situation. So in January 2019, there was the first fire. You can see a vehicle on the left. That was a small sedan car. And then in 2019, again in September, there was a big fire where you had a truck with papers in the back, being able to, the ability was to come in and then detect the fire and then have the fire crew coming in and make an intervention. So it's very, very important to say that the system behaved quite very well, and it exceeded everybody's expectation. From a trial point of view, these pictures on the top can show, yes, you can get a pre-alarm, you activate the camera, and then you have a sprinkler system. At the bottom, we can see a real-time event and real problem happening in this real world. And the EGMT, which is the #1 tunnel in America, and then you have firefighters being able to come in and intervene while the fire is being suppressed. Extremely important. The second application is conveyor belt monitoring. Conveyor belt monitoring is an interesting one. We get a lot of fires because the idler bearings overheat, and these bearings can cause a lot of damages because once a fire is there, you have a wood pellet or you have a different type of material that can catch fire. The ability to monitor the temperature using the fiber optic linear detection. So you have the cable that can go around the bearings and then come down and go to every structure. Each one of those bearings can be monitored. What normally happens is you can monitor the temperature over time, and then if the temperature is increasing too fast, I give an example here in this picture, exponentially, you can set up alarms in a very, very strategic way. You have a pre-alarm that says, if you reach this temperature, something is wrong with the bearing. Send somebody to go there and check it out. The second approach is, if the temperature is going way, way too high, you can set an alarm. Either you can activate a suppression system. It's very rare for conveyor belt, but at least you can stop your conveyor belt. So if the alarm is triggered, you can stop the conveyor belt and then go and check. This is before a fire happened. It's not a fiber optic linear detection is now used in this case for detecting just a fire, but it can also be used for preventative maintenance. That is not the case for conventional linear detection. The conventional one, as I talked earlier, you either have a preset system that tells you the temperature or the rate of rise. But if you have any of them wrong, you are not doing what you're supposed to do, which is preventing a fire. You can have power cable trays monitoring as well. Here's an example of pictures where you can run the fiber optic cable within a cable tray, and you can tell the temperature of the cables, medium voltage, high voltage, you name it. But you can also go to an elevator shaft and then be able to monitor the temperature as well. So from a sensing point of view, you can stop a fire and you can activate an alarm before it's too late. An example of a fiber optic cable tray approach is, here's on the left is a mine in Latin America, for instance, where you have a splice box. And this cable tray is in a tunnel. The ability to be able to monitor each one of those rows is very important. Number one is the fire detection connection, fiber-optic linear detection. The second thing is to be able to monitor the temperature within the tunnel. In that tunnel, you can see the human beings walking in there. You can activate the fan to say the tunnel is too hot, the cables are overheating, send an alarm to activate the fans within the tunnel. The second thing is to be able to stop any human being going within that tunnel because it's too hot. It's very, very versatile in terms of the ability that the system can do. Another application is airport hangar. Hangars are very interesting in the sense that the asset that we're monitoring is probably as expensive as we can get. Here's an example of a airport hangar in Chicago. You have one system that's monitoring up to 2 kilometers mounted on the roof and tied in on the picture on the right. You actually can see the fiber optic linear detection controller tied into the fire panel. It's very, very important. On the left, at the bottom left, is you can see why this is such a critical asset. Is that every time an hangar gets installed or set up, that means the airport is growing. At the same time, we are monitoring these new assets, which are planes. 737 is the example on this case. The mayor of New York, of Chicago, is there, Manuel, and you can see in this application that the fans, the sprinkling system has to be activated with our linear detection and the IR cameras and IR sensors. Foam is very, very expensive, so you can literally pinpoint where the fire is happening, and then you can actually flood the system. We have parking structure as well. Here's an example of where you have the roof of a parking structure. The roof of the parking structure is ensuring that you can monitor the temperature at many locations. But most important, fire detection point of view, you don't need to bring physical point sensors. The point sensor heat detectors can be very costly in the sense that you have to wire each one of them, put them strategically in the right locations. With the fiber optic linear detection system, you can easily just run a cable, set up your zones virtually, and the ability to tie into the fire detection panel. On the right, you can see this is a fiber optic linear detection controller tied in the old fire detection panel as well. Floating roof temp is an example. This is a very, very good approach of using fiber optic linear detection, because we are not just a detection system, we also can tell you if you're overheating. In this case, on the right, you can see there's a fire on the left, on the right-hand side, and then this tank is on fire, but it's also affecting the other tanks. If this tank is burning so much, this tank will take over as well, and then start burning as well. So the ability to be able to put a fiber optic linear detection cable on the roof tank and understanding where exactly, pinpoint that it's coming from the left side, right side, or if you look at the quadrant system, you can actually activate the foam, which is a very, very expensive system, at the right location or flood the entire tank. Here's an example of why it's very important, is that you can also look at the other tanks, the adjacent tanks, and be able to flood the other tanks before these other tanks are affected by the tank on fire. In this case, is the software showing exactly that. So if there is a high temperature at this location, you can flood this tank number 2, and then you can flood tank number 3 as well to make sure that the fire is not expanding. Power generation facilities. You have facilities where the cable can be where you have different temperatures within different rooms. The ability to change and to be versatile enough to monitor up to, let's say, 15 zones or 1,000 zones. You can have switch gears. This is an application where we did 15 zones. You have switch gears rooms We have transformer chambers, we have powerhouse ceilings, we have powerhouse service levels, we have draft tube gallery, we have so many different assets that can be monitored, at the same time different rooms that can be monitored. And you just run one single cable. In this case, in this picture, you can see the cable coming up to the structure, mounted horizontally, vertically this way, horizontally. We changed the alarm setting for this area because there is a motor running in this case, and you're also going to the venting system, and there's a big fan, and we changed the alarm parameters there. The ability to buy a system and say, I don't know what the alarm level is going to be from a temperature point of view, and I can set it up on the go. That is the beauty of fiber optic linear detection. We also have done, in my opinion, one of the coolest projects is a concert hall. This concert hall is very challenging in the sense that you can go to an opera house, with one of the most prestigious opera house in Europe, and the ability to pinpoint exactly, because the ceilings are too high, and you need to know exactly where the fire could be coming from, and flood that particular area is extremely important. The challenges are, you want to avoid the fire to spread. You have about 500 people in the room, and you want to limit the damage of the water as well, because when you're flooding the area, you can do a lot of water damage. Here's an example of, in the picture on the right, where you run the fiber optic linear detection, and then you can run in each one of those rows, and that's what we did. And the ability to pinpoint within the rows which seat is the one affected by fire is very important. To take it to the next level is similar to the Eisenhower tunnel. We call this performance-based. Why is it called performance-based? At the end of the day, there is a lot of regulation, but if you're not sure about the regulation is meeting what you have to do, you go back and you do a trial and do a test before selling your alarm. Here's an example of the picture on the right. They tested an area, they tested a seat, and to know and detect what is the temperature level, what is the rate of rise that can be happening at that location. And then you can say, we move forward to the project, and they installed it everywhere. And the ability to set this alarm based on the performance that was done prior to the installation is quite important. So in terms of value, you have a short sampling interval, you have a short measurement cycle, you have a sensitivity to alarm parameters that are precisely defined and set up for this particular application. You are not just going with the standard, let's say, regulation. The regulation might be wrong, but as long as you are testing the system, you can monitor everything else. Thank you very much. If you have any questions, I'm really open for them now.
Thank you very much, Julio, for a very informative presentation, and really great work on behalf of the Technology Committee in promoting this particular aspect of fiber optic sensing. For those who are listening, if you want to ask a question, there's a box on your right, and you can type that in, and I'll relay that. But let me lead off. Could you give us a little sense of the number of systems that have been installed so far, in what regions are they the most prevalent, and how does the US stack up against some of those applications?
Thank you, Mark. It's a very, very good question. Up to today, the beauty is that the installations have been, at least we're looking at 8,000 installations. In the case of our company, maybe 5,000 installations or 4,000 installations. What's very important in this sense is that in Europe, there's a big fire in the Mont Blanc years ago, and that fire was quite a catastrophe in terms of human loss, and as well as damages to the tunnel. That this regulation has been pushed within Europe so strongly. In America is learning more about it, and it's unfortunate, but we don't need to have accidents before we start making a decision. In the US, we particularly still work with a lot of transportation company, as I showed in Colorado and other areas. The goal is to make sure that everybody is aware of what's going on. It's interesting. In the US is also behind Asia. All the tunnels that are being built in Asia today have this system installed, because it's not just about knowing exactly that you have fire, you know the location, and you know the direction of the fire. The direction of fire is very important, because you can shut down the tunnel and evacuate in certain areas, and you can open certain exit door within the tunnel to make sure that human life is minimized in terms of loss. So we are going in the right direction as well in America, but it's taking a while.
Could you give me a little sense of how fiber optic sensing relates to some of the building codes? Obviously, building codes are real drivers for where particular systems or particular requirements. I'm assuming that one of the benefits is that this is does a better job or is more precise, but could you kind of provide some color on that?
Yes, so in terms of building code and requirement, and I talked about UL and ULC and then FM Global as well. You have different codes that says if you reach, let's say, up to 10 meters in terms of ceilings and areas, you can measure a temperature up to that point. What makes us and other vendors very, very accurate is the ability to understand that it's not just a maximum temperature that meets the code. UL and ULC are what I call best practices. Yeah. You have the NFPA 72, you have different NFPA 507, which is another one for tunnels. Those are standard practices, but they can differ from a tunnel to another, from a hangar to another. We meet the code precisely. We standardize the system in such a way that the controller and the cable is meeting the UL rating and approval. So whether or not we meet it is great, but I would like to go beyond just the certification approval. This system is so amazing in the sense that we can continuously improve these codes as well. We are changing the systems. We're not going on conventional systems. We are updating, and I hope we can continuously help in terms of maintenance, installation perspectives, everything else around the codes that's existing today. We're helping improving that.
That's very helpful. Actually, I have a follow-up question from one of our participants that sort of, conceptually a follow-up question. We've talked about the Eisenhower Johnson Tunnel. Are there other fire detection systems that were included, such as flame detectors or other automatic fire initiating devices? So I guess that in relationship to that is the question of how does this system interact with other systems? Are they included, or does fiber optic sensing stand alone?
In this case, as I showed this, the Eisenhower Tunnel has been a beautiful story in the sense that it's been a performance-based system. Based on the test that was done, there was no requirement to use any other system, period. The fiber optic was able to understand rate of rise and maximum temperature. To take it to the next level is, if you think about a tunnel and there's traffic within the tunnel, there can be a truck with a big exhaust fan overheating an area. And if you buy the wrong conventional linear detection, you get an alarm, you're done. In this case, the fiber optic, the client was able to understand that if there's a traffic within the tunnel, I can change my alarm system. And that's the beauty. We were the only detecting system. That's it.
And I guess the next question is perhaps a clarification. I think sometimes we need to kind of explain a little bit about how fiber optic sensing works. So the question was about sending signals wirelessly to a controller, or do you have a hardwire connection? So you may want to kind of explain a little bit about how the system works.
Yes, so the cable is installed within the structure or within the area you want to detect the fire for.
Right.
And then it's connected to the controller. The controller can be powered by a 24-volt UL system or battery, that's next to the fire panel. What's very important is that this controller can be connected as well with any kind of Ethernet router or wireless router to send this data wirelessly as well. So from a point of view of installation, you have a lot of flexibility. You can put this system in one end of an infrastructure and be able to send the data wirelessly, or you can also do a standard networking as well.
And I guess the sort of natural follow-up question to that is, if there's a break in the fiber optic cable, can the system continue to function?
Yes, as I showed in one of my slides, we certainly don't want these breaks to happen. This is actually the beauty about the system. At the end of the day, if a break happens, you can monitor up to that point. And as I showed in one of my slides earlier, the ability to understand that you are now losing coverage. And an example of a tunnel is it costs money to have a tunnel shut down, and it costs people a lot of troubles. In this case is an example where this cable was able to detect up to that point when the break happened.
And following up on the break question, I had a question about how easy is it to replace damaged cable, and also related to that, a question about the ability to do testing or inspection, which basically trying to activate the system to make sure that it's still functioning.
Yeah, so very, very good question. We do, because we're a temperature sensing system, every year in every installation we've done, you can come in and monitor the temperature. It's quite important, and the accuracy of the temperature can be done not even within the rooms you want to try to do it, but you can test it in different areas within the sensing cable system. Getting back to the question about how is it easy to replace, it's very simple. If a cable is broken, you remove few meters or inches or feet of that area, and then you can bring in a new cable and do a fiber optic splice. This fiber optic splice is very simple. The connectivity is also quite simple in the sense that when you do this splice, it's not a new zone. It's the same zone as you had before, and the system is still continuous.
Got it. So following up, I know we talked about the Eisenhower tunnel, Eisenhower-Johnson tunnel, and the fact that it was fiber optic sensing was a standalone system. Could you talk a little bit about the integration of fiber optic sensing with existing systems for suppression? Is that, how feasible is it? How does that take place, where perhaps people are looking for a belt and suspenders solution?
Yeah. This slide pretty much depicts the beauty about the system. We have up to 106 relays output that can connect each one of those zones. We can go even beyond that. So in this similar project, we had at least 200 plus zones where the relay output can tie into the fire panel, activate not only just the extinguishing system, the suppression system, for that particular zones, which is very, very amazing. We can pinpoint within a meter which zone to activate. So you're saving water, you're saving foam, you're saving everything. And in this case, it's more water. The second approach is you can also have a pre-alarm to activate a camera. And that was the exciting thing about this project, is the integration is so simple and so seamless, and we are not tied into any other systems. We are very, very flexible to make sure that the goal of extinguishing, the goal of suppression is done in such an easy way.
That's good. Are there any safety concerns when you're using fiber optic systems, perhaps with the laser?
Yes, that's a good question. I'll give an example of explosion-proof areas. We tune these systems to have the laser to be particularly activated in such a way that there will be no problem when, let's say, somebody break the cable. There's no problem with the lasers. As a matter of fact, the conventional system is much more dangerous because it's an active system where there's electricity going through these wires. In the case of fiber optic linear detection, the laser has almost, I'd say, no threat in terms of damages and potential damage, but yet we have to meet the requirement for, I give an example of floating tanks where you have fuels. If a cable breaks and the laser is too powerful, it can have a problem. But this is why we meet the requirement of EX, IEX, zone 1, zone 2, zone 0 approval.
Have any systems been installed in conjunction with an aspirating fire detection system in order to maximize early fire detection capabilities?
Yes, so I'll give an example. I've done projects where you have aspiration systems that were known to be the fast response systems. But these fast response systems are fantastic in beautiful controlled environments, where we have replaced, even, I won't say in conjunction is not the right term, we have replaced these systems because they are extremely bad in industrial environment. The fiber optic linear detection is now worried about dust and everything else. We don't need to purge the system. We are monitoring the temperature, and we can monitor the rate of rise. So in response to aspiration systems are fantastic, but in a very controlled environment. Our system is not standard to this type of environment. It's very industrialized, and we can monitor the rate of rise, the maximum temperature as fast as or as good as this aspiration system in different applications.
And next, how close does the fiber optic cable need to be in order to, sort of how sensitive is there, and how far away can it pick up anomalies, fire anomalies that are taking place?
The two approaches here, and there is the conventional approach, is you go to the standard of UL and put an installation based on the common practices. In the case of other applications, like conveyor belt, for instance, is a perfect example. You want it as close as to the asset that you want to monitor, because you're caring about rate of rise, you're caring about heat buildup. So sensitivity has to do with the medium, the size of the space, and we design every system accordingly, or installation. Yeah.
So in a sort of building context, how much fiber do you need to be able to put in? And can you detect across the building, or do you need to be in within a particular distance in order to pick up an issue?
Similarly to what we discussed about tunnels and other places, it's very important to say that you can run this fiber as simple as running a wire across a building and be able to detect the fire, to know about exactly what the temperature. As long as the building is not, let's say, 3 feet long only, you'll be okay, because the spatial resolution is within a meter or 3 feet. It's very simple to run the fiber optic linear detection and be able to detect it up to certain areas.
Okay, that's been very helpful. I think that's the last question I have. I will just kind of let everybody know that this presentation will be available through our Fiber Optic Sensing Association website, probably within a few hours, but at least not longer than a day. It'll also be available on our YouTube site, as all our prior presentations as well. We're very pleased to announce that in December, we will be having a presentation from Schlumberger, which is one of our new members in the last 6 months or so. So we're looking forward to that. We'll have more information posted on the details of that shortly. And just a reminder for our members, we will be having our annual meeting in Washington, D.C. of the first week of December, and we're looking forward to participation at that. So congratulations, both Julio and Gareth and the rest of the Technology Committee, for sort of an excellent job on demonstrating one of the really emerging and very promising applications for fiber optic sensing. And that concludes our webinar.
Thank you.